நான் இன்ட்ரோ கொடுத்துறேன் சார், அதுக்கப்புறம் நீங்க உங்களுக்கு இன்ட்ரோ கொடுத்துறேன் சார்.
Okay.
Once again, I welcome the participants and professors and all the persons who are involved in the webinar for the day 2 second session. This person's chairperson is Dr. B.R. Venkataraman, Assistant Professor of Chemistry, Periyar EVR College, Trichy. The resource person is Dr. Kannan Ramaiyan from USA. On behalf of Chemistry Department and Periyar EVR College, I thank both the speakers and chairperson of the session. Now I hand over the session to Dr. B.R. Venkataraman.
Thank you, Dr. Tanigachalam sir. Good morning to one and all present virtually. On behalf of PG and Research Department of Chemistry, Periyar EVR College, Trichy, I welcome you all for the day 2 and session 2 of the 2 days international webinar on research evolution towards current scenario. First of all, I thank our respected Principal Madam, Dr. J. Sugandhi, respected Head of the Department, Dr. C. Thangavelu, and dear organizing secretaries, Dr. C. Pragadishwaran and K. Tanigachalam, for giving me an opportunity to chair the session. It's a great honor and pleasure to introduce this session speaker, Dr. Kannan Ramaiyan. Currently, he is working as a research assistant professor in the University of New Mexico, USA. Actually, he's having a very rich biodata. So I'm mentioning here only few events and achievements of his career. He did his schooling at Tanjavur. He completed his BSc Chemistry at Raja Sarfuji Government College, Tanjavur, and MSc Chemistry at Bardhasan University, Tiruchirappalli. He completed his PhD Chemistry from a premier institute, which is a CSA-funded lab, National Chemical Laboratory, Pune. He had an astonishing employment history. Initially, he was a technical trainee of Dr. Reddy's Laboratories, Andhra Pradesh in 2004. Then he pursued a postdoc in University of Calgary, Canada in 2011 to 2013. He worked in University of Birmingham, UK in 2013 to 2035 as Marie Curie postdoc fellowship. He served at Central University of Tamil Nadu. Again, he did a postdoc in Los Alamos National Laboratory, USA in the year 2016-2020. He is the recipient of many grants, which worth lakhs and crores for his projects, which includes Marie Curie Fellowship funded by European Commission in 2013, LDRD exploratory research funding by the Los Alamos National Laboratory, USA in 2019, and funding from Feynman Center for Los Alamos National Laboratory, USA. He carried out a successful market research for his patented mixed potential electrochemical gas sensors that resulted him for a commercial call in July 2019. He is a recognized reviewer of more than 15 reputed journals like ACS Catalysis, Journal of Materials Chemistry Section A, and International Journal of Hydrogen Energy. His research involved mainly in the development of electrochemistry laboratory for meeting the present and future energy requirements. His research area is functionalized carbon nanotubes based composite membranes for polymer electrolyte fuel cells. He received many awards from national and international research foundations and chemistry bodies such as Kirti Sangoram, NCL, and Marie Curie fellowships. As a mentoring scientist, he has guided more number of students and scholars across globe on the research topics of perovskite, electrocatalysts, and fuel cells. His teaching career had touched the popular institutions like Central University of Tamil Nadu, Tiruvarur, University of Birmingham, UK, and University of Calgary, Canada. He is the, mainly I want to mention here, he is the holder of 2 US patents. It's a very tough job to have a US patent, and author of book and published more than 4 research articles in highly impact factor journals, international journals, and presented his research findings in various national and international conferences. He also invited as a research person to share his expertise. In a nutshell, he is an extraordinary scientist with enormous activation energy who have converted many models into successful products. Such an eminent scientist with us today to enlighten us. And also, he is very humble. I just talked to him. He is very simple. And I request Dr. Kannan Ramayan to take over the session. And dear participants, please post all your queries in the YouTube chat box. Over to Dr. Kannan Ramaiyan. Thank you.
Thanks a lot, Venkataraman sir. Thanks a lot for this wonderful introduction. I did had 1 or 2 slides for my introduction, but now I will skip them all. Can I share the screen?
Yes, share the screen.
So you are seeing the full screen, right?
Yes, yes, Dr. Kannan, it is visible only.
Okay, perfect. Thanks a lot, Venkataraman sir, and thanks a lot, Dr. Thanikachalam, for giving me this wonderful opportunity to present my work. I'm working as a research assistant professor at the University of New Mexico, as sir already described. I have planned my talk in this following manner. I thought I will give an initial introduction about me, but I think that's not necessary anymore. I will also give a small introduction to the electrochemical technologies that are expected to be revolutionary in the near future. Then I will move on to fuel cells and its components, and I will talk about the composite electrolytes, which is my area of expertise. And I'll also give its current status, where the technology is and what it needs in terms of development for reaching commercial marketplace, and what are the further requirements in terms of research for this technology to be enabled in the commercial space. I'll be happy to take any questions after that. Yeah, these slides can be skipped now. I was born in Pacifico, did my PhD in NCL. I have about 900 citations. So I'll move away from those introductions. I want to start my technical presentation with the famous quote by Nobel laureate Wolfgang Pauli: "God made the solids, but the interface, the surface, is the work of the devil," because the surface never obeys the bulk property. Surface is always different from the bulk. And when we are talking about the electrochemistry, we are dealing with not just one surface, but we are dealing with the 2 surfaces called the interface. When an electrode is inserted in the electrolyte, the surface charge on the electrode as well as the ions present in the electrolyte, they realign themselves to form a double layer. This double layer theory was first, okay, I will also take this. Yeah, so this double layer theory was first introduced by Helmholtz in 1853. After that, there were quite a few modifications to this theory to get the diffusion layer and the diffuse double layer, compact layer, Stern layer, all these layers into the to incorporate all these things into the theory. But basically, the double layer is the key when we are talking about electrochemical processes. This is where all the reactions taking place, whether electron transfer or charge storage or double layer forming, everything is taken care at the electrochemical interface, and that we will see how that interface is playing a crucial role. So the first technology I wanted to show is the electrochemical supercapacitors. So when we talk about normal capacitors, when it is charged, it will have one layer of positive charge and the other layer of negative charge separated between them, and that will define its capacitance. And that's the end of a regular capacitor. But when we are going for a supercapacitor, the electrochemical capacitor, because it has 2 electrodes, it can have double the number of charge storage right away. And another thing is the electrodes can have a huge surface area, and because of that, it can store enormous amount of energy. if you want to say a simple example, a regular capacitor is like a cloth. If you wanted to wipe the surface of, if you want the water from the surface, you can just use the cloth. But if there is a lot of water and you use a sponge, how the sponge will absorb a lot of water, like that, because of its high surface area, the supercapacitor can have a huge capacity. So that is the biggest advantage of supercapacitors. If you look from the Helmholtz double layer charging principle that came in 1853, this technology should be a no-brainer, or it should be the first thing that research scientists should have come up with. But it was the last one among the electrochemical technologies to come up. The technology was first invented in 1957, and the commercialization quickly followed in 1975. And the next one is the batteries. Today, we all know what batteries are. Without the batteries, I think our lives are no more. So the batteries were first invented in 1800 by Alessandro Volta, and it got its first commercial product out in 1898, about 100 years. So in the supercapacitors, the the electron never moves from the interface. So electrons don't move from the electrode to electrolyte, but in batteries, the electrons actually move from the electrode to electrolyte. So an actual chemical reaction takes place, and because of the capacity of the batteries are much higher than that of a supercapacitor. The next one is fuel cells. The fuel cells were first invented in 1839 by Sir William Groove, and it was used in the Apollo Gemini spacecrafts in 1960. It was made into commercial cars in 2007, but it is not yet widely spread. So why do we need these technologies, or why these technologies are gaining new interest, or why why this talk is relevant for this particular symposium? Because we are living in a burning planet. The global warming is basically destroying our planet at this moment, and we cannot sustain the current rate of consumption of fossil fuels. We needed to find an alternative energy conversion technology, and if we are going in the same way with consuming fossil fuels, the carbon dioxide levels are increasing so fast. We were being told a few years back, once it hits the 400 ppm, the climate change will be irreversible. We have already crossed the 400 ppm mark. The Arctic ice is quickly declining. As you can see, the solid black lines are actual measurements, and you can see the ice levels are quickly declining. And if it continues this way, in 10-20 years, we will reach a situation where we will be in an essentially ice-free situation. That time, most of the continents will be flooded with water. More importantly, the another most important parameter in this is the perishable fossil fuels. So if we are continually using the fossil fuels in the way that we are using, the oil and gas will be gone in 30-40 years, while the coal may be sustaining for another 100 years. So we need to find alternative technology. So what are we doing in terms of preserving our planet? Well, historically, we are moving away from a carbon-rich fuel to a hydrogen-rich fuel. In the 1800s, in India, even in 1900s, we were still using wood as the major source of energy. Wood contains about 10 to 1 of carbon to hydrogen. And then we switched it to coal, which is 1:1 between hydrogen and carbon. In the 1950s, we switched to oil, which has a higher hydrogen ratio in comparison to carbon. Today, we are using mostly gasoline or methane, which is 1:4 carbon to hydrogen ratio. So it only looks like a matter of time that we will be using a completely carbon-free hydrogen as the fuel. If we are going into that situation, why do we need fuel cells? So there are quite a lot of energy conversion devices. Why we need to look for fuel cells? If you remember the previous slide, among the three electrochemical technologies, fuel cell is the only technology that directly converts the chemical energy stored in hydrogen into electricity. So this is positioned primarily to harvest the energy of hydrogen into electricity. Fuel cells, if we are looking into this animation, converts hydrogen in the fuel cell. Hydrogen comes through the anode, reacts with the catalyst to form protons and electrons. The electrons goes through the external circuit to give you the current, and in the cathode, the protons and the electrons combine with the oxygen to give you water. So it's a very simple process, does not involve any greenhouse gases. Only byproduct is water and heat. It gives you an open circuit potential of 1.23 volt, and it has a high energy, and it will be a wonderful technology if we can sustain it. What are the other benefits? If we are looking at the traditional combustion engine based vehicles, they are controlled by the Carnot efficiency, but fuel cells, since they convert the chemical energy directly into electrical energy, they are not controlled by the Carnot efficiency. So the efficiency of fuel cells can be much higher even at room temperature. They provide you a cleaner operation and reduced emissions. And because fuel cells can be modular, you don't have to have a centralized power grid, so you can easily decentralize the power grid into rural areas, and also it provides you a silent operation. So what are the fuel cell components? If we are looking at a fuel cell, there are four main components. The bipolar plate, where the incoming fuel is distributed through flow fields to the electrode. And in the electrode, there are two components. One is the gas diffusion layer. It performs the role of allowing the fuel to go close to the membrane, and also provides another means of excess byproducts to leave the system. And then there is the catalyst layer, where the actual electrochemical reaction takes place, and you have the membrane where the protons are transported from one side to the other side. But at the same time, the membrane should be electronically an insulator. It should not allow any electrons to cross over, because if it happens, then it will be a shorting and you will not get any electrical current in the external circuit. So it has to be an electrical insulator, but electrochemically it should conduct the protons from one side, the anode, to the cathode. My work comprises of improving the electrolyte performance. So from now on, I will talk about my work. So when I started research on polymer electrolyte fuel cells, at the time, even today, the state of the membrane is a Nafion membrane. It has polytetrafluoroethylene backbone, and it has a sulfonic acid side chain. This sulfonic acid side chain, when it is allowed to contact water, it will form hydrophilic domains. The hydrophilic domains area is calculated to be 4 nanometer, and it is interconnected by hydrophilic channels that are 1 nanometer. So these hydrophilic domains are the key for the proton conductivity of Nafion. So for achieving a good conductivity for Nafion based membranes, you needed to have high sulfonic acid content, as well as you needed to have a very good water content. When you have both of these, then it will provide you a very good proton conductivity. Unfortunately, the negatives of this membrane, because it relies on water, you cannot operate these membranes at a temperature above 100 degrees centigrade, as they will quickly dry out. And also, the membranes have a poor or moderate mechanical stability, so you need to improve the mechanical stability for getting a better durability in a long-term operation. If you are looking for a commercial device, you want them to perform at least 2-3 years, unlike our smartphones, which go bad in every 6 months or 1 year. These fuel cells, one would want them to perform for a long periods of time. So it needs mechanical stability as well as chemical stability. So in that respect, we had a simple idea. So as we know, the Nafion has a polytetrafluoroethylene backbone, and it has a sulfonic acid side chain. We were thinking, we basically tried to functionalize carbon nanotubes, which is one of the durable material on Earth. We tried to functionalize this carbon nanotube with the sulfonic acid groups on its side chain, and tried to make a composite with the Nafion. The idea is, because of the excess sulfonic acid in the Nafion, it should have a higher proton conductivity. At the same time, due to the carbon nanotube presence, it should have a better mechanical stability. So that's what we were thinking when we were making this composite. Let's see if that worked out. So first thing, how we prepared this sulfonated carbon nanotubes. So we used a simple microwave treatment where we mixed 1:1 ratio of concentrated nitric acid and sulfuric acid, and microwave treated to produce carboxylic acid as well as sulfonic acid functionalized carbon nanotube. When we wanted a phosphonated carbon nanotube, we further treated them through a thionyl chloride route with the aminoethyl phosphonate that resulted in the phosphonation of these carbon nanotubes. So first we will see the composite membranes prepared between the sulfonated carbon nanotubes and the naphthalene. So when we made the composites, we wanted to first see what happens to the hydrophilic domains. We saw the hydrophilic domains in the naphthalene is about 4 nanometer in size. So the small angle X-ray scattering measurements helps us to calculate what is the hydrophilic domain size in the naphthalene membrane in a composite as well as in the pristine membrane. So we measured it and we found that the domain size was increasing from about 4 nanometer to about 7 nanometer when we incorporated the sulfonated carbon nanotubes. And also the proton conductivity increased from about 27 millisiemens per centimeter to about 35 millisiemens per centimeter for a very small amount of carbon nanotube addition, something like 0.05%, 0.058% added carbon nanotube, we could get the proton conductivity increase from about 27 millisiemens to 36 millisiemens. So the hydrophilic, and you can see there is a direct correlation between the hydrophilic domain size as well as the proton conductivity. Next step we wanted to see is it actually helping in improving the mechanical stability aspect. So as you can see, we tried the naphthalene membrane first. The recast naphthalene membrane had a much inferior mechanical stability in comparison to the composite membranes. Our composite membranes showed much better mechanical stability than that of the recast naphthalene membrane. So in the previous slide, you could ask this question. Well, you are adding the sulfonated carbon nanotubes. Why there is a drop in conductivity beyond a particular point? You are saying only 0.05 and 0.05 and 0.1% addition helps to increase the proton conductivity, but further addition of carbon nanotube actually decreases the proton conductivity. Why? That question comes, right? So that's where the other parameter in the naphthalene proton conductivity controlling parameters, the water. So when we add more carbon nanotube, what happens is because of the carbon nanotube, the membrane becomes stiff, so it cannot absorb more water, and the water content in the membrane starts to go down. And because of that, the resulting proton conductivity is also going down beyond a particular limit. So these results were well in correlation with what we observed. So next step is to see these improved proton conductivity as well as mechanical stability actually helped us to get a better fuel cell performance. Before going into the fuel cell performance, I wanted to show you how a polarization curve look like. What are the areas of a polarization curve? So this is how a conventional fuel cell polarization curve would look like. This is basically the cell voltage. Previous 2-3 slides before, I was showing why fuel cells, and we were looking at a theoretical open circuit potential coming from the thermodynamics as 1.18 or 1.23 depending upon what temperature we are operating. But invariably there will be some loss when we are actually operating in a fuel cell setup. So the actual fuel cell open circuit potential will be slightly lower than that of the theoretically predicted value. This could be due to the mixed potential or the gas crossover from the anode to cathode or cathode to anode. Then there are 3 regions. One is the first region will be a sudden drop that is due to the activation losses. To activate the electrochemical process, there will be a huge price to pay for. So this is the activation loss. Then the second region in the polarization curve is called the ohmic polarization, that is due to the membrane resistance. If the membrane is very good, this will be a pretty much a straight line instead of a slopey one. Then the third region is mass transport. So if your membrane is really good, if your electrochemical process is happening so fast, there comes a situation where you are not able to supply the reactants fast enough to the electrochemical interface. So you are no longer able to sustain the reaction rate, and that's where the final drop in performance will happen. So this is called mass transport limited area. So these are the 3 regions of fuel cell performance curve. With that in mind, I will switch to my polarization curves we observed for my work. As you can see, the recast Nafian membrane showed about 250 milliwatt per centimeter squared fuel cell performance and about 600 milliampere per centimeter squared in current density. But when we made composite with sulfonated carbon nanotubes, you can see the power density was continuously increasing, and it reached a maximum of 370 milliwatt per centimeter squared for the 0.05% carbon nanotube composite, further increasing the carbon nanotube content apparently decreased the fuel cell performance, and we already know why, because of the poor water content. The second figure in this particular slide is the solid state cyclic voltammogram we observed for all the uh, 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 cells that we are showing in this particular figure. This is basically to show that in this particular figure, this particular area is due to the platinum content in the membrane. If the fuel cell performance can be altered by adding more platinum also. So we wanted to show we didn't add too much platinum. The platinum levels is constant in all the tested membrane electrode assemblies, and the performance enhancement is solely due to the improved membrane characteristics. So that is why we needed to run this measurement to prove that our performance enhancement is solely due to the improvement in membrane characteristics. So we could achieve a total of 50% improvement in fuel cell performance with our composite membranes. The next question in our mind is, well, we had a strategy. You wanted to improve the Nafian's performance. The key for Nafian's proton conductivity is sulfonate groups. So you functionalized the carbon nanotube with the sulfonic acid groups. You made a composite. You improved the performance. Is this strategy also applicable in other membrane systems? So we wanted to see that. So for that purpose, we chose polybenzimidazole membranes. In the polybenzimidazole membranes, phosphoric acid is the key for its proton conductivity. When it is doped with the phosphoric acid will help to conduct the protons from one side to the other side. But because it absorbs so much phosphoric acid, at some stage its mechanical stability will be poor. But what are the advantages of these PBA membranes? These membranes operate at a much higher temperature, unlike the Nafian membrane that operates at temperatures below 100 degrees centigrade. The PBA membranes operate at temperatures above 100 degrees centigrade. So we want, because of the higher temperature operation, the kinetics can be much better, and we don't have to worry about managing the water content of the cell. In the Nafian-based membranes, if too much water is produced, it will flood the cell and it will decrease the performance. But in the case of PBA-based membranes, we don't have to worry about water because we are operating at a temperature higher than 100 degrees centigrade. So all the water formed is in the gas phase and it will be easily removed from the system. And it also gives one more advantage. You can use higher carbon monoxide containing fuels. If you are looking for hydrogen is everywhere, but not as such. So you need to reform hydrogen from either hydrocarbons, or you need to hydrolyze water electrolysis to produce hydrogen. If you are electrolyzing water, the produced hydrogen will be absolutely clean. But if you are reforming from hydrocarbon, it can have a higher carbon monoxide content. And because of this higher carbon monoxide content, it can poison the platinum electrocatalyst used in the fuel cells. Because in the case of PBA-based membranes, because we are operating at a temperature more than 100 degrees centigrade, it has a higher tolerance towards carbon monoxide. So with that in mind, we tried to prepare phosphonated carbon nanotubes and made composites with PBA membranes. And we wanted to, I'm not going to show all the data that we observed. I'm just going to show you the mechanical stability and polarization measurements. As you can see, without the carbon nanotube addition, the pristine PBA membrane had a much lower mechanical stability in comparison to all the composite membranes. And in the case of polarization measurements, again, as we can see, the pristine PBA membrane gave about a 600 milliwatt per centimeter squared performance. But when we are switching it to composite membranes, the 1% doped PBA membrane showed about 780, almost 800 milliwatt per centimeter squared. So we could take the simple methodology of functionalizing carbon nanotube and making a composite. We showed that methodologies work in Nafion-based membranes. We also showed that methodologies work in PBI-based membranes. So we believe that we have showed a wonderful methodology to improve form a composite and improve composites performance with carbon nanotubes. With this methodology in the PBA-based membranes, we achieved about 30% improvement in fuel cell performance. So this will be the third work that I'm involved. This is the most recent work which I did in Los Alamos National Lab. We were trying to work with intermediate temperature fuel cells, and we still were trying to find a better electrolyte for operating in the intermediate temperature, somewhere about 200 to 220 degrees centigrade. And in the about 2006, this type of material came into the fore, where tin pyrophosphate based materials showed high proton conductivity in the temperature range of 200 to 250. But the one problem with this tin pyrophosphate is that it's not a dense material, and because of that, forming a dense membrane without the hydrogen crossover. Hydrogen will cross, if it's a porous membrane, the hydrogen will move from one side to the other side, and because of that, it will create a lot of shorting, and you will not get a good open circuit potential. To avoid that, we tried to form composite between tin pyrophosphate and Nafion, and I'll show you what we did with that particular experiment. So when we were preparing the tin pyrophosphate, what is the precursor that we are using? That determines what is the particle size we are ending up with. So there are, in the literature, most researchers were using a phosphoric acid as the phosphorus precursor, and either tin sulfate or tin chloride as the tin precursor, and they were invariably sintering them at about 650 degrees centigrade to prepare the tin pyrophosphate. So what we did is we tried to vary the precursor material. We prepared 5 different precursors. We used simple phosphoric acid. We also used phosphoric acid and ammonium hydroxide. We used diammonium phosphate as the phosphate source. We also used trimethyl ammonium phosphate as the phosphate source. And we also tried to use tetrabutyl ammonium phosphate as the phosphate source. As you can see, in the case of phosphoric acid, we used the oxalic acid in the preparation procedure. Only in the diammonium phosphate, there was no oxalic acid used. In the case of tetrabutyl ammonium, there is this huge tetrabutyl group that acts as the hydrocarbon content. And we will see how this hydrocarbon content affects the final prepared TPP powder's morphology. First thing first, we wanted to show that in the crystallography, all these structures were formed properly. So as you can see in the XRD pattern observed for our materials, all the 5 precursors provided a cubic tin pyrophosphate phase. And when we used only the oxalic acid as the hydrocarbon content, all the powders were white in color. But when we used tetramethyl ammonium phosphate or tetrabutyl ammonium phosphate, the powder was gray or black in color. The black in color was due to the unburnt carbon that was forming something like a graphene oxide, and we don't want an electronic conductor in the electrolyte, so we did not do any further experiments with the tetramethyl ammonium phosphate based powders, tin pyrophosphate powders that we have obtained. So as you see from the scanning electron microscope, when we used the phosphoric acid as the precursor alone, it formed very well-defined particles, but the particle sizes were about 500 nanometer. When we used when we prepared the TPP with tetrabutyl ammonium phosphate, the particle sizes were brought down to about 150 nanometer in size. So the concept that we were finding is, when we were using the oxalic acid, that completely burns off about 200 degrees centigrade. Because of that, the formed TPP particles had about 400 degrees centigrade to sinter well, and because of this time, the particles were sintered into bigger particles. But in the case of TBAP, where the tetrabutyl ammonium group is not burning off at a very low temperature, it is burning off only close to 550 degrees centigrade. The particles did not have enough time to grow, so we could get very small nanoparticle size, 150 nanometer sized tin pyrophosphate. And this particle size played a crucial role in uh, getting a denser membrane. So we were trying to form a composite membrane between this tin pyrophosphate and a naphthalene. We were using a high concentration of the tin pyrophosphate, which is 90%, and we were using only 10% naphthalene. Because the particle sizes were huge in the case of phosphoric acid based precursor, you could see that we got only a porous membrane. And as the particle size decreased from the tin of phosphoric acid based powders to tetrabutyl ammonium phosphate based powder, you could see that the porosity of the membrane was constantly decreasing, and the TBAP based membranes gave us a very dense membrane. So the dense membrane invariably should result in a higher performance. And as you can see from the fuel cell performance, the open circuit potential we observed for the TBAP based TPP powder was close to 1 volt, which is significantly higher than that observed for all the other powders, that all the other composite membranes where the particle sizes were bigger and the membranes were porous. Because of that, the open circuit potential that we observed for those composite membranes were much lower in comparison to our TBAP based TPP composite membranes. Also, as you can see, the power density, the phosphoric acid based membranes gave about only 250 milliwatt per centimeter squared, whereas our composite membranes with TBAP, it gave about 350 milliwatt per centimeter squared. In this particular case, the thickness of the membrane was close to 150 micron. So we decided to decrease the thickness to improve the conductivity further. And as you can see, by decreasing the thickness from 150 to 50 micron, we could increase the power density from about 350 to about 620 milliwatt per centimeter squared. And also we could reduce the high frequency resistance, the overall resistance of the fuel cell from about 250 ohms per ohm centimeter squared to about 100 milliohm centimeter squared. So we basically showed through this small in the presentation, I showed you 3 different composite membranes. I tried to form, one was a naphthalene sulfonated carbon nanotube composite that performed better than the pristine naphthalene membrane. Then we also formed a phosphonated carbon nanotube with the PBI, and there also the composite showed much better performance than that of the pristine PBI membrane. In the third example, where the tin pyrophosphate based fuel cells were struggling to get a higher open circuit potential, but we made a small adjustment in the precursor, and that helped to improve the open circuit potential to a higher value and also get a much higher fuel cell performance. So despite all these improvements from our group as well as across the world, what is restricting the fuel cells from commercialization? That's the next question that the fuel cell industry is facing. Well, the first thing would be the cost. When we are looking at a small scale production, the cost is coming from the catalyst. The catalyst used in fuel cell is platinum. Platinum is expensive and also scarce in the earth. So the catalyst plays a crucial role. Then bipolar plate, also the membrane. But the membrane, when it is scaled up, because it's a hydrocarbon, it could be brought down up to 9%, but the catalyst price is actually going up because platinum is not abundant on earth. So if you are trying to use more platinum, the platinum's cost is going to go up. So cost of the membrane, cost of the fuel cell is one major issue. And why the cost of fuel cell is very high? Because of the use of platinum. So if someone could come up with a better catalyst that is non-precious metal based, basically a iron or a cobalt or iron cobalt alloy or some other cheap metals, that would be a great incentive for this technology. The second problem with this technology is creating a hydrogen infrastructure. Um, Basically, in the United States, where we like to claim we are the leaders, but it's not the leaders in this particular field as of now. It has only 39 publicly available hydrogen refueling stations. And if we are looking at the entire world, we are having about 273 publicly accessible refueling stations for hydrogen. If we are comparing that with refueling petrol, like if we are looking at a petrol pump, in India we have about 60,000 petrol pumps, and if we are looking at United States, the United States has about 160,000 petrol pumps in the US. So 160,000 and 39. That basically gives us the picture why the fuel cell is not yet coming into the commercial marketplace. We needed to create a better hydrogen infrastructure, but creating a hydrogen infrastructure is not easy because the hydrogen is a very small molecule, and a traditional stainless steel based uh, tubes cannot be used for transporting the hydrogen across the country. In the United States, there are quite a lot of pipelines that transport the um, natural gas. Even in India, we all probably were hearing about the shale gas pipeline project from Kerala to Karnataka, where we are basically using stainless steel based tubes. Like that, in the United States, there is about 1 lakh kilometers of pipeline already available for transporting natural gas, but you can't use them for transporting hydrogen from one part of the country to the other part of the country because of its small size, and it will easily penetrate through, and it will make the stainless steel brittle. So that's one major issue that restricts. That is the other major issue that restricts the commercialization of fuel cells. So the two major issues that faces the fuel cell industry is the cost and hydrogen infrastructure. Okay, so I have told quite a bit of negative news from the global warming, carbon dioxide levels going up, Arctic ice going down, or the having a poor infrastructure for hydrogen. Let's go for some good news. Or what are the future research direction that should look like if you are looking at an electrochemical energy conversion technologies. All the energy in the world is basically coming from solar energy. If you are talking about coal, it is basically solar energy stored millions of years ago in the coal, right? Everything is photosynthesis helps you to make plant, and the plant buried, you get coal or oil and all other stuff. So instead of digging them out, we should find a way to harvest the solar energy directly, and for that, electrochemistry is best suited to harvest the solar energy and convert it into chemical energy. So we can basically try to convert nitrogen into ammonia, or we can convert the carbon dioxide into hydrocarbons, or we can electrolyze water into hydrogen. So these are the three major areas of research right now the world is focusing on. If we could find a better catalyst or better electrochemical process to carry out this research, it will be a groundbreaking research in this particular field, and that will basically change how we are viewing, how we are spending our energy every day. It will bring down everything. So in that line, ammonia is not just energy storage fuel; it can also act as an infrastructure fuel. In the United States, there is about 5,000 kilometer of ammonia pipeline already exists, and you can use this ammonia in the natural gas pipeline also. And very recently, in 2018, a Australia-based group demonstrated that you could power a hydrogen fuel cell car directly from ammonia tanks. So you transport ammonia across the country, and when you are having the need to refuel your car, you can use the ammonia to produce hydrogen on the site. This invention has made the advancement of this technology much easier. This technology is currently trying to get into the commercial marketplace, and quite a lot of patent related things are going on. And you can see this is the ammonia pipeline map in the United States. More than 5,000 kilometers of pipeline already existing, and the remaining natural gas pipelines can be easily converted. But the problem with the ammonia being an infrastructure fuel is that you still produce ammonia with the Haber-Bosch process. Haber-Bosch process uses quite a lot of energy, so we needed to find an alternative way, an electrochemical methodology to produce ammonia. So this is a very recent field. In the last 3 years, quite a lot of publications are coming on the electrochemical synthesis of ammonia. I published one paper in the start of this year where we used a molybdenum carbide based electrocatalyst for producing ammonia. Our synthesis rates were much lower in comparison to what the commercial rate should be. So the commercial rate for producing electrochemical ammonia, commercially viable rate for producing electrochemically ammonia is about 10 power minus 7 moles per centimeter squared per second. But most of the literatures right now dealing with 10 power minus 9 or minus 10. So we are at least 2 to 3 orders of magnitude lower than what is required for electrochemical synthesis of ammonia. Again, this technology is also hampered by the electrocatalyst development. If any of us could come up with a better electrocatalyst, this technology can enable the fuel cells very soon, much sooner than anyone would expect. If we are relying on a purely hydrogen-based infrastructure, I would say this technology would never come. Most of the electric vehicle people basically write off the fuel cell technology because of the lack of hydrogen infrastructure. But this technology, the innovation of the on-site hydrogen from ammonia is one of the biggest innovation in the recent time, and this technology has basically fast-tracked the fuel cell industry at least by 10 years. And once we find a way to produce ammonia economically viable rates, this technology will help hugely to get the fuel cells. So in summary, fuel cells are here to stay. There will be all, if you are going on further to study in this direction, you will see discussions or arguments or even heated fights like in Tamil Nadu between Tala and Talabadi. There is a huge group between fuel cells and batteries. Battery research community will say batteries will be the next, and fuel cell community will say fuel cell community will be the next big thing. But they both are going to be there, and fuel cell will invariably be the one that will power our future cars in very soon. Some of the recent developments. So I was saying platinum was used as the catalyst in fuel cells. When the Apollo and Gemini spacecrafts sent into moon in 1960, the amount of platinum used was 28 milligram per centimeter squared. Today we are using less than 0.1 milligram per centimeter squared in a fuel cell. And non-precious metal-based catalysts. In 2018, one group published a paper where an iron-based catalyst was shown to perform as good as platinum. The problem with that research is still getting the durability. So the iron-based and non-precious catalysts also very close to reaching the targets that are met by platinum-based catalysts. The hydrogen infrastructure problem could be solved in no time if the ammonia synthesis could be scaled up much higher. So electrochemical technologies will be there, and they have the potential to power our future. With that, I thank you all for your attention, and I will be happy to answer any questions. I wanted to acknowledge before that Dr. Tanika Salam and Dr. Venkataraman for giving me this opportunity. And I also want to thank my past and current mentors. And yeah, thank you for attention, and I'll be happy to take any questions.
Thank you so much, Dr. Kannan Ramayan. In spite of you lost your sleep, actually you told, you told midnight is there. Your excellent presentation, and we have overwhelming responses from our participants. Due to time constraint, I will take two questions which asked by participants. Professor Gayatri Ravikumar, ma'am asked about regarding the IEC and proton conductivity. In her point, IEC is directly proportional to proton conductivity, but some reporting it's a reciprocal one. What's your view, sir?
So ion exchange capacity is directly proportional to the proton conductivity, yes, but too much of ion exchange capacity. So if we are looking at the Nafion itself, so the Nafion backbone, the polytetrafluoroethylene backbone, that determines what is the equivalent weight of the membrane. If the ion exchange capacity basically comes from the side chain sulfonate groups. So if the backbone size is decreased, it will increase the ion exchange capacity. But the problem is the membrane will lose the mechanical stability. So the backbone is the one that gives the mechanical stability for Nafion-based membranes. So when you are trying to increase the ion exchange capacity beyond a particular point, the membrane becomes soluble because of too much hydrophilic groups. It will be soluble, and you are dealing with water in fuel cell all the time. So ion exchange capacity, it does directly correlate to the proton conductivity, but because of the solubility related challenges, you cannot increase the ion exchange capacity on a linear scale beyond particular limit. So it's not inversely, but beyond a particular point, it will start to act as a deteriorating parameter due to the mechanical stability concerns, not due to proton conductivity related concerns.
Okay. Thank you for the explanation, sir. Another important question, Professor Muralidharan asked, how do you rate Nafion zirconium phosphate composite membrane in comparison to tin pyrophosphate Nafion composite membrane and Nafion silica composite membrane in terms of performance? Professor asked.
Yes, so that's a very good question. The zirconium phosphate as well as the silica based membranes, they don't have higher higher ceramic content. So in those membranes, the literature, if we see, the Nafion content will be like 80 to 90%, whereas the or more than 90%, whereas the zirconium phosphate or the silica content will be like 1%, 2%, 5%. And those membranes operate at the maximum up to 120 degrees centigrade, 120 degrees centigrade. But this one, it has 90% ceramics. The Nafion is basically there as enabling medium. It's the Nafion is not the source of proton conduction in the tin pyrophosphate Nafion composite, whereas in the other two cases the questioner asked, there the Nafion is the medium of proton conductor, and in the Nafion, as I said, two things that control the proton conductivity. One is the sulfonic acid group, the other one is the water content. So the zirconium phosphate as well as silica, they are highly hygroscopic, so they retain the water at a slightly higher temperature as well. So those membranes operate at temperatures above 100 degrees centigrade up to 120. That is the biggest advantage for those composite membranes. But the TPP, the tin pyrophosphate based membrane, here Nafion is not the one that is providing proton conductivity. It's the TPP that is providing the proton conductivity. Nafion is only 10%, that only is acting as the matrix for putting the TPP powder in the composite. So they are totally two different systems. TPP operates at about 220 degrees centigrade. My slides were my performances was taken at 220 degrees centigrade, whereas the zirconium phosphate or silica, those membranes operate at the maximum up to 120 degrees centigrade. Yeah, so that's pretty much the differences.
Thank you so much, sir, for your explanation. And I think due to time, next session is going to start. With this, once again, I thank you very much on behalf of organizing committee, on behalf of chemistry department of Periyar EVR College. In spite of your busy schedule and you lost your sleep today also, I thank you very much. I thank you very much on behalf of all participants.
Thanks a lot.
And we have wonderful presentation now, which is a hot topic today. As you said, simply Tala and versus Talabadi. fuel cells versus battery. It's a very good explanation, sir. Thank you very much, Dr. Kannan.
Yeah, thank you. Thank you.
Over to Dr. Thanikachalam.
Shall I leave?
Shall I announce that?
Yeah, you announce, sir. No problem.
Yes, sir.
No, I will leave. Huh?
Okay.
Hello.
Next, no, I will leave. Okay.
Oh, okay.
Oh, yes, sir. Yes, sir.
Thank you.
Okay.
Thank you.
Thank you. Thank you, sir. Thank you, Dr. Kannan. Thank you. Dear participants, due to the speaker, Dr. Sugumar Venkataramani, his unavoidable and emergency academic work, the third session of day 2, that is the final session of day 2, has been preponed to after this. So please, dear participants, please stay in the same link for the third and last session of this international webinar. The chairperson for the last session is Dr. A. John Amalraj. Thank you all. Thank you. Over to Dr. Thanikachalam.
Dear participants, please stay on the same link. No need to go for your further or third link. You may please stay on the same link. Our third session's speaker, Dr. Sugumar, also in online. We may continue our session. The third session's chairperson is Dr. John Amunraj, Assistant Professor of Chemistry from Periyar Ivar College. And the speaker is Dr. Sugumar Venkataramani from IISER Mohali. I welcome you. I welcome both speaker and the chairperson. Now I hand over the session to John Amunraj, sir.
Hello.
Sir, audible, sir. You may speak, sir.
Okay, sir. Video is not there, sir.
Sir?
Hello. Video.
Sir, speaker also on the line, sir.
Okay, okay.
You continue, sir.
Okay, okay. So good afternoon to all. With great pleasure, I would like to introduce our research person, Dr. Sugumar Venkataramani, Assistant Professor of Department of Chemistry, Chemical Science, Indian Institute of Science, Education and Research, Mohali, to enlighten this session with his innovative thoughts under the topic further insights into reactive intermediates. So regarding education, he did his undergraduation at the ABC College, Mayiladuthurai, and master's degrees at Baridasan University, Trichy here. He obtained the doctoral degree in the field of natural science at Charles University, Germany. So regarding in research, he has published more than 50 international papers with high impact publications. Regarding awards, he received many awards. So one of you I have to deliver. So in the year of 2008, he received for the award of Alexander von Humboldt Fellowship, and he has completed JR of National Eligibility Test NET. He has produced a number of PhD students under his guidance. At present, 13 research scholars of doing research under his guidance. He is multi-talented research person and also a suitable research person for this delightful session. Once again, I welcome our young, challenging personality, our research person, Dr. Sugumar Venkataramani. Now I hand over the session to our research person, Dr. Sugumar Venkataramani.
Yep. Thank you, Dr. Amalraj. Actually, I must thank Dr. Thanikachalam for inviting me and also to the other organizers. And before going to the session, actually, I apologize because I needed to take one meeting in the afternoon. So that's why I requested Dr. Thanikachalam to prepone the session. Sorry for the inconvenience, basically. What I'm going to talk in the next 45 minutes or so is based on the reactive intermediates. This is one of the research area what we are dealing with at IISER Mohali. And of course, we are part of a physical organic chemistry group. That means we are working on some of the unstable species. So part of our lab is concentrating on one project where we are dealing with unstable cis isomer of azobenzenes. So in the other side, we are also dealing with some of the reactive intermediates. So in this particular talk, I'm basically talking about this reactive intermediates project. And I try to make it as the level of the talk as low as possible. I want to introduce the topic by using some kind of sports events. For example, there are 4 pictures which are depicting some of the commonly occurring sports events. One is the high jump, other one is pole vault, and the third one is this long jump and the triple jump. So if you connect, if you want to connect this to chemistry, there are some interesting aspects. Basically, in the high jump event, there is a horizontal bar that is basically the barrier. So normally, if you want to cross the barrier, the athlete has to put some efforts. So basically, they have to increase their energy, and then they have to cross a barrier, and then they can lower their energy so that they can come to the ground. So this is something very similar to the reactions also. And in some cases, if the barrier is even higher, then the simple efforts from the athlete is not sufficient. So they need to use some kind of pole so that they can jump this barrier. So if you connect the same thing, if you understand the biomechanics involving the long jump, they are trying to increase the energy, and at some point they have the maximum energy before they are losing, so that they are coming to the ground. So that way they can go to the longest distance possible. And in the case of triple jump, they are basically rising their energy and lowering to the minima, and then again rising the energy and then coming to the minima before coming to the maximum distance. So basically, if you look at this, they are something similar to the parabolic curves. So here, in the first event, there is a parabolic curve where it is reaching a maxima before coming to the lower energy. And here, this is also the same case, but before that, there is a use of pole vault. So if you connect these aspects with chemistry, then in the first case, this is particularly the uncatalyzed reaction. But if you are using a catalyst, then basically you can overcome a huge barrier as well. So this is something similar to the catalyzed reaction. And if you come to the long jump, basically this is something similar to the concerted reaction. And if you come to the triple jump, this is something similar to the stepwise reaction. So all these concepts are related to the energies. So now, if you connect the energy versus the reaction channels, then you will be ending up with something called energy profile diagrams. So normally for energy profile diagram, you have the reactant and you have the product. Normally the organic chemist will be always targeting new products. So they will be starting with the n number of starting materials, and they will be ending up with this product. For any reaction, the reactant has to overcome certain barrier before coming to the product. But when you consider the reactions, there are 2 important physical concepts. One is related to the thermodynamics, and another one is related to the kinetics. So for thermodynamics perspective, this is nothing but the relation between the reactant and the product. So that is represented by the free energy changes. Normally the delta G naught, that is the free energy changes. If it is negative, that indicates the reaction is more facile. So that is exothermic reactions. On the other hand, there is a barrier, and if you relate the barrier with the reactant, then that is called the free energy of activation. And this free energy of activation is required for any reactant to overcome the barrier before reaching the product. So at the barrier, there is one more species that is called transition state. So far it is very clear, reactant, product, they are very clear. But when you come to the transition state, it is a kind of imaginary species. It's not easy to visualize. If you want to visualize, so I want to demonstrate with this particular sports event where you have seen this badminton. So here there is a shuttlecock that is being hit from one end by a particular player, and the cork is moving. But during the process, what happens? It will be reaching the other side, where you will be always seeing some kind of orientation where the cork is always coming to the player. rather than the feather. So why does that happen? So normally the shuttlecock has an uneven mass. So basically the mass is more residing in the cork, and feather being a lightweight, when it is being hit, it will be trying to move faster, but eventually the energy has to be distributed across all the places. During that process, the feather will be undergoing a tumbling so that the cork is moving and it is coming to the opponent's end. So this is where the tumbling happens. So this is where if you consider as a reaction, the transition state also will be appearing. So normally the transition state is connecting the reactant and the product in the reaction coordinate, and that is something similar to a vibrational motion. So when the vibration is towards this side, it will be resembling the reactant, and if it is crossing this barrier, then it will be resembling the product. So normally the lifetime of the transition state is also in the lifetime of any vibrations. So that's how you need to connect between the reactant and product. So this is something very similar and very simple in the case of concerted reactions. But when you come to the complex reactions, you will be always ending up with multiple transition states. That means the reactant and products are connected by two transition states at minimum. And if there are two transition states, there is one more minima that is nothing but intermediate. So if you have such kind of systems, then basically you have two different free energy of activation. And among these two free energy of activations, whichever is the larger, then that is corresponding to the reaction which is the barrier, real barrier. That means they are at the reaction rate determining step. So the other one, once the intermediate is formed, the barrier is lower, so it can easily overcome the barrier and ending up with the product. So these are something related to the stepwise reactions. So if you want to go for the stepwise reaction, the key species is the intermediate. So now we understood something about the reactant, product, and transition state. The next important thing, what we need to understand is the intermediate. So now the question is, what are intermediates? So normally if you go to any organic chemistry lab, you can see some of these kind of species. So this is isocyanate, ketene. So this is orthophenolic methide, and this is the ortho and paraquinomethide and ylides. So these are some of the key species which are formed during the reactions. And in principle, you can isolate if you are able to follow certain mild conditions. So now these are kind of isolable intermediates. So you can even stock these intermediates under milder and also inert conditions, as long as no nucleophile is interfering. So that way you can able to get the stabilized intermediates. On the other hand, there are certain intermediates which are quite unstable. So these are nothing but your reactive intermediates. So these are some of the examples like phenyl radical, benzene, carbene, and nitrate. So this you have already come across in your organic chemistry. Anyway, these are the reactive intermediates which I am going to discuss about in this lecture. So now, if you want to understand the reactive intermediates, one of the most important part is to go for the understanding of types, or if you have to do classification. For classification, normally the reactive intermediates are generally done based on their charges. Majority of the reactive intermediates are neutral. Of course, some are charged. So the best examples are the carbocations, carbanions, radical cation, and radical anion. So if you see some of the examples, so this is a phenyl cation, so you have a positive center, and you have the benzyl cation, so this is the positive center, and this is the resonating structure where the cation pi cloud that can be delocalized in principle. And there are other charged species that is negatively charged, then that is carbanion, where the carbon center is negatively charged. And these kind of carbanions are more stabilized if you have a electronegative atom which is adjacent to this. So normally if it is in the 1,3 position, then that will be having a delocalized carbanion, then that will be more stabilized. On the other hand, you can easily come across these radical cations. So these radical cations are commonly occurring in mass spectrometry. So normally, if you want to understand a mass spectrum, you have to generate this kind of radical cations. So basically, you are ionizing the molecules. So that time you are removing one of the electrons. So then you can generate one unpaired electron and one cationic center. So in these kind of systems, that will be more stabilized, and you can able to get the mass by charge, and using that you can get the molecular mass of the systems. And another important species is the radical anion. So for radical anion, this is one particular example where the benzophenone, if you're adding sodium, then you can end up with this kind of radical anion. So why this system is important? So I can explain you. Normally, if you're using certain reactions like Grignard reaction or using the butyl lithium based reactions, you need to use some very dry solvents. For example, dry THF or a dry hexane, this kind of solvents. If you want to go for drying, normally what you need to do, you have to remove the water. So for that, initially you can dry with some kind of dehydrating agent like calcium chloride. But that is not sufficient because there will be some trace amount of water will be always present in the form of moisture. So if you want to remove that, you have to use sodium. So normally sodium is extremely reactive with water. So normally the pre-dried solvent will be added with the sodium in the form of wire. So the wire, why wire means this is having a larger surface area so that it can extremely reactive with the water which is in contact with the sodium. And also you will be adding benzophenone. Why the benzophenone is being added? Normally what happens, if the sodium is reacting with water, it will be converting into sodium hydroxide with the liberation of hydrogen gas. Once water is removed, basically reacted with the sodium, now the sodium can add one electron to the electron deficient benzophenone. So during the addition of electron, what happens? You're generating a radical center here, and since the oxygen is electronegative, it will be converted into anionic center. Now the sodium with the loss of one electron, it will become Na+. So the whole system is this radical anion, which is counterbalanced by this sodium plus. So now the importance of this species is this can be solvated and that will be having a specific color, something like purple to blue color. In case if you are drying the system, if you are reaching this blue or purple color, that indicates there is no moisture in the solvent. So basically you are trying to achieve this by adding the benzophenone and sodium and refluxing the solvent. During the process, this is acting like an indicator. So once this is reached, then you are understanding that there is no more water or no more moisture. Then you have to distill off the solvent so that you can get the dry solvent. So that's how the drying is happening. So these are basically charged reactive intermediates. When you come to the neutral reactive intermediates, there are plenty of examples. So some of them are radicals and biradicals and benzynes and carbenes and also nitriles. So here you have at least neutral charge. Basically they are having no positive or negative charge. They are electrically neutral. And on the other hand, they are reactive intermediates. So basically you have classified the reactive intermediates based on the charge. There is another way of classifying the reactive intermediates that depends on the location of the orbitals. So basically the orbitals in which the radical center or cationic center or anionic centers are residing. So based on that, you have basically three different or most important types of classification. One is sigma orbital, in which the reactive center is located. The best examples are the phenyl cation, phenyl radical, and also the benzynes, these kind of examples. And some cases, you have the location of the reactive centers at the pi orbitals. So the phenoxy radical, benzyl cation, or the xylonyl cation radicals. So these are basically some of the examples for pi-centered radicals or pi-centered reactive species. So another type of classification is a mixed type of sigma and pi orbitals. So basically in the nitrene you have one sigma and one pi orbital involved for the two unpaired electrons. And this is the phenyl radical. So if you are combining a phenyl radical with nitrene, then you are basically generating the sigma and pi type reactive intermediates. So here also this is carbene, where one unpaired electron is a sigma and another one is pi. So basically you have two orthogonal orbitals in which the two unpaired electrons are residing. So those kind of things are providing some additional aspects about the reactive intermediates. Why this is very important is because they will determine the three important aspects. One is the stability of the reactive intermediates, and the other one is the spin-spin interactions. Basically, if you are having a biradical, how the two unpaired electrons are interacting with each other. So that is one of the decisive factor, particularly with respect to the spin multiplicity and the ground states. So sometimes two radical centers within the same molecule that can be either leading to a singlet or triplet. So if you want to understand whether it is a singlet or triplet, you need to understand this spin-spin interaction. So before going to spin-spin interaction, I just give you some glimpses on the stability aspects. For stability, normally the reactive intermediates can be classified into three types. One is stabilized, another one is persistent or stable type reactive intermediates, and the third category is transient reactive intermediates. So if you want to understand stabilized reactive intermediates, it's very straightforward. So basically the triphenyl methyl radical, this is the first isolated radical species that was done in 1900 by this famous gentleman, Gomber, and he made this molecule. And this particular triphenyl methyl radical, of course, he was mentioned that this is a radical, but in fact, after several years, people understood that this is not existing as a radical alone, but it will be always exist in an equilibrium with its dimer. But of course, the dimer is not having a bond between this carbon and another carbon of the radical center. Instead, this is reacting with one of the other molecules of phenyl group. So that's how the dimer is happening because of the steric reasons. So this is one of the stabilized radical. So why it is stabilized? Because this radical center is located at the benzylic position. So that means this can have an extended pi conjugation. So it can have several resonance structures. So that means it will be more stabilized because of resonance. And on the other hand, there are some reactive intermediates, they can be stable and they can be extremely stable, and in fact it is one of the laboratory based reagents, and in some cases it can be generated and it can be stabilized for several years also. For example, this N-heterocyclic carbene developed by this Arduino, it was stabilized because of this bulky groups. This adamantyl group is stabilizing this nucleophilic carbene. So that carbene is extremely useful for catalysis, and this can be stabilized. And this is another radical. This is a DPPH, diphenyl picryl hydroxyl radical. This is one of the EPR standard. So basically, this radical is stabilized because, once again, due to the aromatic pi conjugation and our resonance conjugation. So this is also stable, and this can be available commercially as well. And this is, of course, a tempo well-known radical, and it is being used for radical trap and also identification of reaction mechanisms in case if any radical is involved in the reactions. And of course, these two are stabilized or stable reactive intermediates. And another classification is based on the transient evidences for the radicals. So in case if the reactive intermediates are forming and instantaneously reacting, then those kind of reactive intermediates are transient reactive intermediates. For those species, you cannot directly characterize them. For example, this is known by crystal data. So basically the crystal structure is available. And for this species, it's commercially available and we can readily use. But in the case of transient reactive intermediates, you cannot isolate them. So how to get to know the existence? You have to go for some other method. So one important reaction is this chlorobenzene. When it is treated with potassium amide, then it will form the reactive benzyne. So if the benzene is formed, then the nucleophile, an amine nucleophile, can attack either this carbon or this carbon. So basically you will be ending up with two different products. But if you want to understand whether this is happening, one of the carbon can be having a C13 labeled. So if you react this with the potassium amide, then what happens? Now the two carbons are unequal. So one is C13, another one is C12. So now if you undergo the reaction, what happens? You will be always getting this mixture of products. The amine is substituted at the ipso carbon where this is C13, or the ipso carbon is C12. So using this, we can able to identify the intermediacy of benzene. So these kind of reactive intermediates are supposed to be transient reactive intermediates. Right now, this is based on the classification. Of course, I will discuss about this at a later stage about the reactive intermediates, which can also be characterized by some other means. But when you come to the other important aspect, which can govern the radical stability and also some important aspects related to the spin interaction. So for the spin-spin interactions, I'm taking two different examples. The first example is related to the benzene. Normally, the benzene is traditionally known as orthobenzene. So because two unpaired electrons are situated next to each other. And there are isomeric benzenes as well. So this is called as metabenzene. And this is obviously the parabenzene. So now these systems are very interesting because you have two unpaired electrons and they are residing in two orbitals. So that means you have two possibilities. One is the two orbitals are degenerate, and if they are degenerate, Hofbauer principle, Hund's rule will be the dominant rule. So that means you will be ending up with a triplet state. On the other hand, if you lift the degeneracy between the two orbitals, what happens? The Hofbauer principle will prevail. So that will lead to one of the orbitals is doubly occupied and the other one will be vacant. If that happens, then you will be ending up with a singlet biradical. So that means all these three species can able to get either a triplet or singlet in principle. But what will happen eventually is there will be a spin-spin interaction. So basically the two radicals or two unpaired electrons will interact with each other. If that happens, what happens is these are having a bonding interaction or anti-bonding interaction. So normally if it is a bonding interaction, that will be stabilizing, and anti-bonding interaction means that will be destabilizing. So as a result, the two orbitals which are supposed to be degenerate become like this. So one orbital is selectively stabilized and the other orbital is destabilized. So now the two electron has to go to the symmetric combination. So this is how the benzene is supposed to be singlet. Although we can expect a triplet state, but this spin-spin interaction is leading to the singlet ground state. So when you are exciting, then it can go to the excited state. Still, it can be a singlet excited state. But if there is a possibility for intersystem crossing, then only you can achieve the triplet state. So now when you come to the metabenzene, the situation is similar, but only difference is the two radical electrons are slightly far away compared to the orthobenzene system. As a result, the difference between the two orbitals, the symmetric combination and the antisymmetric combination, is slightly lower compared to this system. So compared to orthobenzene, the metabenzene has a lower difference between the HOMO orbital and the LUMO orbital. So that is the major difference in the case of metabenzene. But now if you come to the parabenzene, the distance between these two radical electrons or the orbitals are quite far away. So in those systems, what happens? The reversal of the orbital is happening. That is leading to the antisymmetric combination to be low lying and the symmetric combination to be high lying. Why does that happen? Basically, this orbitals is interacting with one of the carbon-carbon sigma star bond. So basically, the anti-bonding between these two carbons. So if that happens, basically this radical is interacting with the sigma star, and this radical is interacting with this sigma star. So if you want to have such interaction, the sigma star, if it is anti-bonding, then this can be a negative and this is negative, and this is plus and this is plus. So that kind of interaction is more stabilized. And if you have the sigma star and both are plus and one is plus and one is negative, basically the interaction will be destabilized. So that's the reason the symmetric combination is getting higher in energy, and that becomes LUMO, and the antisymmetric combination is gaining stabilization. So that becomes HOMO. But still this gap is narrowed down. Compared to the orthobenzene, the energy difference between the HOMO and LUMO is keep on decreasing. That is because of the interaction. And normally these kind of interactions, spin-spin interactions, leading to all the three systems to attain a singlet biradical. And the major reason for this kind of singlet biradical ground states is because of the two types of interactions. One is called through space interaction, that is the direct overlap between these two radical orbitals. And if the distance is increasing, then the direct overlap is not possible. So that has to happen only through the bond. So that is called through bond interaction. So this is one of the important concepts. Through space and through bond interactions, those are very important for our research, which I am going to discuss in the later slides. And as I mentioned initially, I'm taking another example where the same type of orbital interactions are also deciding factor for their spin multiplicity. In this regard, I am taking this carbines as an example. So normally carbines, you can have a variety of carbines. So in these cases, both are chlorine. Here chlorine, and one side you have methoxy, and here it's phenyl and methoxy. And here another set of carbines where one is electron withdrawing nitrile, and in another case you have olefin or phenyl, this kind of pi conjugated groups. So basically you have three different types of carbines. So one is having electron donating groups, this chloro methoxy kind of groups, or electron withdrawing cyano groups, or pi conjugated groups. So now you have three different sets of carbines. So now if you go to the electron donating carbines, electron donating group containing carbines, then what happens? You have a carbene means there will be one sigma orbital and one pi orbital. So these are the two orbitals corresponding to the carbene center. And you have the non-bonding orbitals, which is coming from the chlorine atom. So chlorine has the lone pair of electrons, so the non-bonding electrons that is interacting. So whenever the non-bonding electrons or orbitals are interacting, so that is selectively interact with the pi orbital of the carbene center. So in that case, the sigma orbital will be will not be influenced by anything. So that will be staying at the same energy level. But the pi orbital, due to the interaction with the non-bonding orbitals of the chlorine, you will be ending up with the two new molecular orbitals. So one will be stabilized and the another one will be destabilized. Normally the carbenes means you have two unpaired electrons. So two electrons from this, and you have one set of pi orbitals which are in non-bonding orbitals. That means two electrons are involved in the interaction with this carbon set. So that means two electrons are coming from this orbital. So effectively you have 4 electrons. So now if you fill those 4 electrons, what happens? You will be filling 2 electrons in the bonding combination and 2 in the sigma. So that means you have essentially a singlet carbene. So that will be, and ground state of this particular carbene is singlet. But now the situation is slightly different when you have electron withdrawing substitution. So now if you take a cyano, what happens? This is electron withdrawing. So you have a pi star orbital that will be slightly stabilized, and pi orbital will be more stabilized. So that will not involve with any interaction with any of these orbitals. But the pi star orbital will be interacting with this pi orbital of the carbene. So now the sigma orbital will be untouched, so that will be staying as such. But this interaction will be leading to a bonding combination and anti-bonding combination. So now what happens? This orbital is very close to the sigma. So in one sense, they are becoming degenerate. So now what happens? The carbene centers have 2 electrons. Since cyano is electron withdrawing and it is involving pi star, so there will be no electron. So that means you have to fill only 2 electrons. So the 2 electrons can be filled in the degenerate orbital, means this kind of carbenes will be leading to a triplet carbene. So basically the electron withdrawing substitution, if it is connected to the carbene center, you will be ending up with a triplet carbene. So now if you come to the pi conjugated systems, if it is connected to the carbene center, for example, I am taking a olefin. So that means you have pi and pi star orbital. So now once again they are interacting with the pi orbital of the carbene. So the sigma, once again it is untouched, but the pi orbital of the carbene and the pi star of the olefin, they are interacting and they are forming 3 new molecular orbitals. So one is more stabilized and another one will be stabilized, and that is degenerate with respect to the sigma, and the other one is destabilized. Now here in this side, you have 2 unpaired electrons from the carbene center, and pi orbital means you will be carrying 2 electrons, and pi star will be having 0 electron. So if you fill those 4 electrons, 2 electrons will be filled in the bonding combination, that is filled, and the other 2 electrons are degenerate. So basically you are ending up with a triplet carbene. So orbital interactions play a very important role in deciding the spin multiplicity of the carbenes. So electron donating groups will be leading to the singlet carbene, and if it is electron withdrawing or the olefins or the pi conjugated systems, then they will be leading to the triplet carbenes. So we are getting some important conclusion from this slide. Basically, the through space and through bond interactions between the orbitals and the other molecular orbital interactions. So these are very important whenever we are going to understand some basic relations about the reactive intermediates and also their existence or their studies and all. So now, so far we have discussed about the characteristics of the reactive intermediates. Now I'm slightly moving to the study part, basically how to study those reactive intermediates. So there are several methods and several techniques have been developed over decades, and one of the important method is to go for spectroscopic evidences. So normally the radicals using the NMR, particularly the CID and IISER spectroscopy can be a very useful technique. And particularly when they are high spin, then IISER is a most important technique. And for carbocation, we can use Raman or NMR. Carbanion also we can use NMR. And carbene, in many cases, we can go for laser flash photolysis. And for nitrene, we can go for IISER spectroscopy. So several of these spectroscopic techniques have been developed after the invention of or characterization of several reactive intermediates by this famous gentleman, Gerhard Herzberg, who got Nobel Prize for that purpose. And of course, these are some of the very trivial methods, but there are non-trivial methods like trapping, like radical trapping with the tempo, or benzene trapping with the furan, or carbene or nitrene trap with the olefins, or sometimes we can also go for spin trap using this nitrosobenzene. So in the this spin trap, what we need to do, we can react this with one particular radical. That radical may be unstable. So if you are reacting with excess amount of this nitrosobenzene, the radical can add across this double bond between the nitrogen and oxygen, So it will form a new radical, that is O-centered radical, and that will be more stable. So once you stabilize the particular radical, then you can able to record IISER spectrum, and then you can understand the structure of this particular part. So using the hyperfine splitting. So that is one method. And other possibility is to go for certain miscellaneous methods like radical clocks, specialized techniques like photoelectron spectroscopy, mass spectrometry, and even in recent times, microscopic techniques is also one of the very important methods. And of course, isotopic label we can always use, and crossover experiments. These are some of the other important methods. But beyond that, there are two important methods. One is related to stabilizing the radicals or reactive species. So George Wolow, he discovered this superacid. So that is nothing but the fluorose, sulfonic acid, and the antimony pentafluoride. Using this, he can able to ionize any species with the certain functional groups so that they can generate the carbocations. And since the sp of 6 minus, that is acting as a counterion, that will form a polymer, coordination polymer, and that will be stabilizing this particular species. So using this, we can able to record the NMR, and we can get the characterization of any carbocations. So for this contribution, he got a Nobel Prize. And of course, another type of set of experiments is to go for time-resolved spectroscopy. So here, one can generate, and at a faster rate, we can characterize these species before this ending up with the reaction product. So in this relevant, Agamemnon Zevail, who got a Nobel Prize in his contribution towards the femtosecond time-resolved spectroscopic developments. So these are some of the advantages. Each one is certain advantages and disadvantages. And if you look into many of these techniques by which you can study the reactive intermediates, there are basically three important approaches. One is we have to enhance the thermodynamic stability. So that means we can stabilize those species with a certain functional groups, which can act like a bulky, or which can enhance the stability by means of resonance. The other possibility is to go for fast detection, something like time-resolved spectroscopy. So at a faster rate, we have to get the information. And yet another possibility is to go for enhancing kinetic stability. So particularly in our current relevance, the social distancing is very important. So basically, the two reactive intermediates are distanced themselves, then basically they can be stabilized. For example, this fruit pulp, so that is stabilized because of the surrounding. So there is no way this can react with another species. Or it can be also achieved by cooling. So basically, the coupling of these two things is what we are going to deal in our method, that is leading to one technique called matrix isolation technique. So this is our setup, what we are using at IISER Mohali. And in fact, we spent a lot of time in setting up this particular technique. Here we have a spectrometer, FTIR spectrometer, and this is the cryostat part, which can be cooled up to 4 Kelvin. And we also need some vacuum systems, and also we need a mixing chamber where we can put our starting materials or reactant molecules, and we need a flow controller which can allow the gases at a specific flow rate. And all these things are needing some sophistication, and we can able to record the spectrum, and then we can do the photochemistry. And for understanding this, I am trying to explain using these cartoons. So normally we have this setup where this is made of KBr, and this KBr we can cool up to 4 Kelvin. So basically we can reach up to 3.5 Kelvin using the cryostat. At this temperature, the KBr basically infrared transparent. We can, if you send the infrared signal, there will be no absorption. So this is completely transparent. So now we are able to deposit certain inert gases like argon, nitrogen, neon kind of gases. Since this is at a very low temperature, once they are passing these gases, they can able to form a film or kind of matrix. Now, if you pass the inert gas, this will not be absorbed by the inert gases. So basically the infrared light will be transparent at this condition. So now with this advantage, we can able to mix our precursor. So the precursor molecule is our gust molecule, which will be diluted in excess amount of our host atoms, that is argon or nitrogen, and we will be depositing. For this, we are taking our sample here, and that will be sublimed. And using the vacuum system, we can sublime at a relatively low temperature. And at this T junction, we will be passing this on argon or neon gases, and these will be diluted, and then it will be sublimed and deposited over this KBr at this position. So now what happens? You will be able to make a matrix isolation. So basically, the gust molecule is isolated and it is surrounded only by the inert gas atoms. So now if you record the infrared spectrum, what happens? Argon and KBr being transparent, we will be getting the IR spectrum only due to this gust species. Since it is isolated, you will be getting extremely sharp signals. And also the temperature is very low, so we can avoid the Doppler broadening or collisional broadening. So all the signals are having its own natural line width. So that is one of the advantages of this technique. So now the next step is to go for the photochemistry. For that purpose, we have a tunable light source. We can use any wavelength, whatever we need. And when we do the irradiation, what happens? The gust molecule can be converted into photoproduct. Once the photoproduct is formed, then if we record the infrared spectra, what happens? We will be getting the changes in the infrared spectrum. So normally, if you compare the before irradiation and after irradiation, you are seeing some new features. So we always do the different spectrum. That means after irradiation spectrum minus before irradiation spectrum. If you do that, then we will be ending up with this kind of different spectrum. So the positive signals are due to the photoproducts and the negative signals are due to the reactant. And using this, we can interpret the spectrum. For interpretation, I want to give one illustration. So for that, I'm taking this particular species, phthalic anhydride. So normally, phthalic anhydride, after matrix isolation, you are getting this kind of extremely sharp infrared features. So this is due to the carbonyl, and this is due to the carbon-oxygen stretching. And somewhere around here, you can expect carbon-hydrogen stretching. So now what we do is, this is under matrix isolation conditions. Now if you do the irradiation, then you will be seeing additional features. So previously there is no feature around this region, but here it is appearing. And the intensity of these signals, whichever is due to the precursor, they are dropping. So now there are several new signals which are other than the precursor. So now if you want to understand this, as usual I explained, we will be taking the different spectrum. So the negative signals are due to the precursor. So they are going down, and these are the new signals which are appearing. So some of the signals which are very trivial, so we can easily understand from their characteristic frequencies. So these are stretching modes of the carbon dioxide, and this is a bending mode of the carbon dioxide. Similarly, we can able to figure out the carbon monoxide, and also we can get new species. This is ketene and water. So the water is some of the impurities which we always get in the matrix. So now if you have certain molecules which can be easily understood, then we have to explain the photochemistry. So now carbon dioxide is forming and carbon monoxide is forming. So that means the cleavage is happening like this way. So that means the remaining molecule is expected to be a benzene. So for understanding this, we used to do the computations. So typically DFT calculations we can perform for the benzene, and these are the characteristic frequencies which is expected at this particular DFT level. And now if you compare with the experimentally observed signals, you can have a very nice resemblance. So basically all the signals which are calculated, they are matching. Of course, there will be some difference in the shifts. That is because this is done at the gas phase, but we are doing the experiments which is surrounded by argon atoms. So that way you will be seeing some kind of shifts. But eventually we obtain this benzene molecule. So this is how we are doing, or we are dealing with our projects. And in our current research, we are mainly dealing with radicals. The radicals, particularly heterocyclic based radicals. The reason is radicals are very relevant for many reasons. In biological aspects, there are appearance of reactive oxygen species, and they have to be controlled by means of antioxidants. So if there is an imbalance, that can lead to oxidative stress, and that will be leading to the damage in the DNA, protein, lipid, and that will eventually cause diseases. So in that sense, there are a lot of radicals that needs to be quenched. And if you want to understand, we need to understand the reactivity and also the electronic structure and also the characterization. These are very important. And some of the radicals are very important in the atmospheric chemistry, because these are very useful reactions which can control the cleanliness of the atmosphere. Sometimes the ozone regeneration is very essential. So those kind of things involve a lot of radical chemistry. And of course, in modern chemistry, there is one approach where we can generate organic molecular magnets. So where if you generate a system by coupling multiple radicals, and if you are able to make sure the direction of the spins are aligned, then you can able to make high spin systems. But this is an extremely challenging project. But if you want to understand these kind of systems, or if you want to develop such systems, this is essential to understand the coupling units, how various coupling units are interacting with the spin, and how the spin and other spin are interacting. So if you want to understand, the radical chemistry is very, very important at a basic level. And another important chemistry with respect to polymers and synthetic chemistry is the raft polymerization, photoredox, and also combustion chemistry. All of these topics really involve a lot of radical chemistry. So in that relevance, we are trying to understand the importance of heterocyclic chemistry. And in that aspect, we have recently published some of the work, which is basically based on the fundamental front. Most of the stuff, whatever I'm showing here, is based on the computations. The reason why we did computations is we were setting up our matrix isolation setup. During that, I wanted my students to get into the radical chemistry using computations. And another aspect is we can get some prior insights before coming to the experimental purview. So in that sense, we worked on several heterocyclic systems, and the importance of those kind of systems are to understand the radical and lone pair interactions. So that is something similar to the benzene, what I have shown before. So in these cases also, we can expect through space and the through bond interactions, and how they can influence the stability of these kind of radicals. So which one is more stable, and which one can be a suitable target for experiments. So that in that relevance, we worked on these kind of systems. And of course, this led to some applications in synthetic organic chemistry. So I'm not going to talk too much into those details. Instead of that, I'm going to give one particular example, which we are currently working on our manuscripts. So this is based on this particular photochemistry of 3,6-diiodopyridosine. So normally, before coming to this particular chemistry, I want to introduce why we are approaching this particular project. For that, I need to introduce this natural product. This is called calichyamycin. So this is the one bacteria-derived molecule. Actually, bacteria can able to synthesize this kind of complex molecule, and this contains carbohydrate units, and also this particular unit that is called ene diene. So here you have a ene and two dienes. So, and this is a trisulfide unit, and this is an extremely rigid system, and these are extremely useful for ene diene anti-tumor antibiotics. So basically, the bacteria is deriving this, and this particular molecule, if it is present in its vicinity, no other bacteria can survive. The reason is this is extremely toxic molecule. So how that does it work? So basically, if any thiol molecule is coming into this, then this will be cleaving this trisulfide. So during the process, this thiol nucleophile will be generated, and then this can attack this particular ring junction. And during that process, there will be changes in the conformations. So that previously it is a rigid, now it is kind of flexible. During that process, the two diene moiety will be coming closer, and that will be undergoing a cyclization. That cyclization is called Bergman cyclization. So if that happens, then that will be leading to a para-benzene type biradical. So if this biradical formed, then this can abstract the protons from DNA molecule. So this lead to the saturation, but the DNA will be losing its protons. That means that will be unstable and it will be eventually get collapsed. So that way the DNA is died and the cell can be died as well. So in that sense, this can be very useful for cancer. So that is the reason people were interested in understanding the this Bergman cyclization and developing new type of molecules which can undergo this kind of moieties. And one of the approaches was to introduce heterocycles as well. So in that sense, our interest was to go for this kind of para-benzene type moiety where two nitrogens are present. And in fundamental point of view, this is very interesting because we have multiple interactions. So you have two lone pairs, they may interact, and there may be radical and lone pair, and this radical and this lone pair are two radical centers. So you have four different types of interactions possible, and all of them will make it more complex. So we want to understand which one is stabilizing and which one is destabilizing, and whether we can able to get this particular species experimentally. So that is our challenge. And another important thing is, if you are taking this para-benzene and if you do the photochemistry, it will undergo retro-Bergman cyclization, meaning that will undergo ring opening to form this ene diene. But in our case, we have two nitrogens, so that means it's an unsymmetrical para-benzene. So the ring opening can either happen at this junction or this junction. So if this junction opens, then you will be ending up with this azo compound. And if this opens, then you will be ending up with this nitrate. So now the question is, which one is really forming? For that purpose, we perform the experiment, and this is our precursor molecule, and this is our computed vibrational spectra for this particular molecule, and this is matching excellent. So we confirm that our sample is in the matrix. Now the next step is to go for the photochemistry. But during the photochemistry, the precursor signals was intensity-wise dropping, and we were able to see new signals. And initially, a couple of signals were increasing, and at later stage, one more signal was increasing. And after understanding the photochemistry rates and all, we understood that there are two important species were forming during the photochemistry. One is this nitrate, and the other one is the fumaronitrate. So the fumaronitrate is forming after certain stage. Initially, only the nitrate was forming. But in the whole experiment, we were unable to see our target species. So another important thing is, this is not opening through this particular pathway. So only ring opening is happening through the nitrogen-nitrogen cleavage. So we want to understand why does that happen. For that, we relied on computations. And what we found out was this para-benzene type analog that is not existing as a minimum. Instead, it is existing in a downhill pathway of the ring opening. So if that happens, even if the iodine is getting cleaved, we cannot able to generate this species, but we will be always ending up with this particular species. So that's what happened. And afterwards, this is undergoing photochemistry, that is cis-trans isomerization to form this species. So for gaining some insights, we did the photochemistry aspects of the computations using the excited state surfaces. And using that, we were able to get the conical intersection. So that is the one which is connecting the ground state potential and the excited state potential, where there can be a degeneracy. And using that, we can able to explain this particular mechanism. And this work was done in collaboration with Dr. Shyam Sundar, who is also part of IISER Mohali, and he's dealing with the computations. So this is one of the project we are dealing at our IISER Mohali. And maybe due to some time constraint, I can stop at this stage, and maybe I can skip the next slides, another project which we are also working on. And I would like to acknowledge my whole group. So majority of the students are here, and of course some students already left. They were doing master thesis, and of course they are the pillars, and they are the ones who did whatever the experiments I showed. And of course I just elaborated the project, but they are the ones who did majority of that stuff. And before finishing, I also would like to acknowledge Professor Satyamurthy, who gave enormous funding for us to set up this matrix isolation facility, and also the former directors, Professor Sarkar, Professor Arvind, and also Professor Gauri Shankar, who is the director in our institute, and also Professor Vishwanathan, who is also one of the experimental expert in matrix isolation, and he was a former head as well. And also I would like to thank my departmental colleagues, collaborators, and also the funding agency. And I would like to thank all of you to show patience and listen to me. And I feel very happy to have questions, and I'd like to happy to answer questions. And I also take this opportunity to invite you all to our campus, which is extremely beautiful and green. And if you have any chance to visit North India, please visit IISER Mohali. And especially students, if any, there are a lot of programs like PhD and in PhD. And if you're interested in, please approach me. I am ready to answer. And if you have any details, please let me know. And I am happy to answer questions if you have any. Thank you very much.
Hello. Can I get the start? Hello. Hello.
Continue பண்ணுங்க sir. Yes sir.
Sir?
Sir, you are audible. Please continue.
Okay, sir. Okay, sir. Thanks a lot, sir, for your wonderful and marvelous presentation of types of intermediates and some how to study the spectroscopy and also the photochemical studies. So the several questions are asked from our EVR college, the PG students. The question number 1. So the comparison of thermodynamical and kinetic studies. So in kinetic studies, the 2 transition states are possible. The number of the transition states occurs, it is depends upon what? First questions. And second one, the delta G1 is greater than delta G2. What is the reason? That is question number 2.
No, actually the number of transition state depends on the reaction pattern. So basically the reaction can happen in the unimolecular way, or it can be happening in the bimolecular way. So that depends on various constraints. I just gave one example where we have used a unimolecular channel where that happens through an intermediate. But the second question regarding the delta G, so once again, this is a kind of example where the first step is a rate determining step. This can be other way around also. But typically, if you are involving a reactive intermediates, the formation of the reactive intermediate step is the rate determining step. That requires huge barrier, because once the reactive intermediate is formed, that can easily convert into the product without much trouble. So the barrier will be usually very small compared to the previous step. So that's the reason the first step is, in majority of the cases, the first step will be the rate determining step.
Sir, another question from Dr. Selvaraj from GD Arts College, Dindigul. Sigma and pi orbital intermediate because of the spin multiplicity. What is the effect of reaction rate?
Usually the pi centered radicals or pi centered reactive intermediates, they are having more stability because they are having more resonance stabilization. So that way the reactivity will be slightly lower than the sigma. Sigma where the reactivity is more confined at that particular centers. So if you take any sigma radical and pi radical, sigma radical will be more reactive.
Okay, sir. Sir, another question, Dr. S. Rajendran from Corrosion Studies from Dindigul. We are using the stable and unstable intermediate compound used as a corrosion inhibitors. Suppose we can using the unstable intermediate compound, which is more effective in the corrosion studies.
Actually,
it is used as a corrosion inhibitors.
With respect to corrosion, I don't know. You need a stable species. I think reactive intermediate may not be helpful. But if the formation of the reactive intermediate is one of the pathways for corrosion, then we may need to address that issue.
Okay, sir. Thank you, sir. Sir, the session hand over to Dr. Tanika sir.
Thank you, sir. Very nice presentation, Sugumar.
Thank you. Thank you very much.
I would like to thank Dr. A.R. sir and you for your nice presentation and question answers. Okay, I think we are at the end of the session of the last session of the webinar. I would like to thank the following persons: Dr. U.P. Sendilkumar, Dr. Balaji, Dr. Edison, Dr. Ramakrishna Sedu, Dr. Kannan, and Dr. Sugumar for their valuable presentation during their in spite of their busy schedules. I think all these people are very busy. You people are very busy, but I could thank each and everyone personally. Within the short time, you people are accept to give a valuable presentation, which could be very useful for all the persons. In particular, PG students ask a lot of questions. In spite of due to the time constraint, we will ask very few questions to everybody. Next, I would like to thank our beloved principal of EVR College and my one more organizing secretary, Dr. C. Pragadiswaran sir. And also I would like to thank the chairpersons of this event, Dr. C. Thangavel sir, Associate Professor and Head, and C. and Pandian sir, and B. R. Venkataraman sir, and John Amulra sir. And also I would like to thank all the staff members of EVR College and non-teaching staff of our EVR College. And finally, I would like to thank Dr. Sendil Kumar, IKSC coordinator of EVR College. But not at least, I could thank my friends Manimaran and Rajiv Gandhi, who made this event perfectly in the background. They helped me in a lot of way to send the emails and collect the feedbacks in correct form and correctly and neatly. And finally, not least, I could thank all the participants. Nearly so far, yesterday, 300 persons, each session is viewed and feedbacked by 300 persons. Today, almost more than 250 persons give their feedback and watch them. Okay, I could thank personally thank each and everyone. I think we will formally end the webinar by national anthem. Thank you, one and all. Thank you.